Welcome to our presentation. I am Shiyu. I am a researcher in Tomb Clinic Rat of ESA and a PhD student in Technical University of Munich. This work is accomplished with my co-authors Hannah, Chris, Benjamin, Julian, and my supervisor Daniel. I would like to present today MultiCam, on-the-fly multi-camera pose estimation using spatial temporal overlaps of known objects. For example, in the operating room scenario, the head-mounted display has very limited field of view. Therefore, we need multiple camera systems to provide useful AR assembly guidance. For multiple camera setup, usually a sophisticated camera calibration procedure is needed. This relies on marker-based system, which makes the application difficult. While on-the-fly pose estimation, we want to get rid of the calibration patterns to ease the use of multiple camera systems. We also want to integrate dynamic and static cameras for multiple view sensing. This can reduce drift error of AR head-mounted display by online camera pose update. There are some related works regarding camera calibration and camera pose estimation. Camera calibration means the measurement of intrinsic or extrinsic parameters based on markers or tracking system. This can be very complex, considering the markers and the actual systems. Camera pose estimation, as an alternative, determines the camera pose position and orientation relative to the reference frame using semantic information in a markerless setup. The state-of-art camera pose estimation can be divided into feature-based approach and object-based approach. Feature-based approach relies on texture in the scene. However, they can fail in the textureless scene, like operating room. In addition, RGB-only approach has pose ambiguity due to missing scale information. The object-based approach is more promising, considering the efficiency. However, the state-of-art approach, like cozy pose, is still far away from real-time. Regarding the related works of object pose dataset, most proposed datasets are single view. We propose a novel dataset for 6 medical metallic objects, including 1 AR head-mounted display and 2 static external cameras with overlapping and non-overlapping setup. This is the overview of our method. In the beginning, there are dynamic and static cameras. There is no overlaps between these cameras. In this case, if there are overlap between 2 cameras, we can update the pose of unknown camera based on the internal SLAM system until the whole system is unified in the same coordinate. Unlike the state-of-art scene graph represented by the dense feature map, we define a spatial temporal scene graph in object level for real-time performance. In the graph, we consider object and camera nodes. The edges are defined as connections between objects and cameras. We assume there are connections between objects and cameras if the objects are observed by the cameras. Based on the overlapping area between 2 cameras, we can update the camera pose. The first step is to get the object pose candidate. From the RGB images, we use the usual architecture to get the object class, bounding box, and key points. From the 2D key points, we can use the Ransack PNP with 3D object surface points to recover object pose. We add dynamic coordinate classification module and 3D loss in the training to enhance the performance of single network. Regarding the scene matching, we consider the scenario where at least 2 cameras observe more than 3 objects. Using object pairs, we can remove object outliers to make the pose estimation more robust. We improve state-of-art matching algorithm by using hierarchical camera structures. We assume 1 camera has known pose with internal tracking SLAM. The other camera can update the pose based on the overlapping objects. We build connection between cameras by spatial temporal overlapping objects. We also propose a novel bundle adjustment approach. We define a probabilistic model based on the observed error in RGB and depth image. Based on the observed error, we can optimize both the object and camera pose via Newton optimization. In this scenario, we assume 1 camera has known pose and the other camera has unknown poses. Based on the predefined Tiger function, we update the unknown camera pose and object poses adjointly. To evaluate our approach, we compare with other previous approach in YCB video dataset. Our approach shows better object detection for similar objects with reduced runtime. Our method also shows better pose detection results and better scene matching with less errors. In our proposed dataset, we evaluate the pose accuracy in near and far distance. We compare our markerless approach with traditional marker-based approach. In near distance, our result is comparable with marker-based approach. The error is around 45.54 mm. We show better result in the case of far distance with error around 50 mm. Our runtime is more than 20 frames per second. Our approach also shows better results than marker-based approach in T-LESS dataset. Our approach can deal with occlusion and cluttered scene. Our trained pose estimator is robust to occlusion, while the marker fails in the case of occlusion. Our scene matching can efficiently filter out object outliers and calculate accurate camera poses. Pose errors rely on many factors. For example, the object size, distance to the camera, and motion blur of dynamic cameras. Usually, large objects show less error than small objects. Object poses are smaller in the scenario of near distance. Our proposed method can efficiently remove the frames with artifacts using the matching algorithm in the case of rolling shutter or motion blur. In this AR demo, we showed one application scenario using our MultiCam approach. In the beginning, the HoloLens is moving in the scene and search overlap with other cameras. Once they find overlap objects, two cameras are connected in the graph. In this example, all the static cameras are well localized in the scene. The user interface provides the user with highlighted tool and instructions. Scene information of object and cameras is the AR application. Summarizing, we show multiple view pose estimation approach is more accurate and robust when compared to cozy pose, and our spatiotemporal scene graph is more flexible and suitable for more application scenario compared to static scene graph approach. In conclusion, our approach and dataset foster real-time and robust pose estimation with AR-guided assembly process. Our work is a promising step towards markerless pose estimation to replace the currently widely used marker-based system. Thanks for your listening.